All right, so let's get going. Any questions about the stuff that I covered the previous time, which was on rules for rewriting relational algebra expressions? So these are what we called algebraic laws, basically allowing you to, in some sense, commute, distribute, push selections, projections up and down the query plan. So those are the sorts of things that we talked about. Now we are going to move on to cost-based optimization. So the goal here is to, given a space of query plans that you can generate by using these transformations, how do you pick the best possible one? Okay, so that's the topic for today. Any questions about the stuff that I covered up until Monday? Okay, so let's get into cost-based optimization. So the idea behind cost-based optimization is you can apply algebraic laws to sort of enumerate many different possible execution strategies or query plans. And the unfortunate thing is that there are many different ways to apply these laws, and therefore many different partial plans which you can assemble together to get more complete plans. And because of that, we need a mechanism that allows us to select good plans. We need a mechanism that will allow us to sort of enumerate all of the plans and then select good ones. Okay, so the focus for us is to look at join trees, and let me describe what I mean by join trees. And so we're going to think about looking at how to compute collections of joins and then assemble those collections to give larger collections. Okay, so a join tree is nothing but a join expression with, you can think of this as with parentheses that indicate the order in which you're going to join these relations. So, and by join I'm talking fairly generally, so this includes natural join, theta join, and cross product. So I'm using join as an umbrella term for all of these operations. So why do I care about joins, and why am I focusing on joins as my sort of primary construct for cost-based optimization? The reason for joins is that this is a super common but very, very basic operation. Joins are costly. Okay, joins are costly unlike selections and projections and scans, right? So selections and projections basically can be inlined within a scan. So you can just do it immediately after a scan, and therefore there is not much you can do in terms of optimizing selection and projections. On the other hand, joins are costly, and reordering and changing the way in which you join can lead to a lot of benefits. The other operations, so things like group by, duplicate elimination, aggregation, are all things that you end up doing typically once you are done with the joins. You typically end up doing as a last step before returning the result to the user. So which is why we focus primarily on joins. So once again, if we can get a good query plan corresponding to the join expression of a collection of relations, then the selections and projections can be handled easily by having them happen at the time you're scanning the relations. So that's an easy part. And the other operations are usually done after the join result is complete. Okay, so that's why we are simplifying the problem and looking at the case of joins as our primary construct. And this is what traditional databases do as well. They focus primarily on joins as opposed to selections, projections, as well as other operations. Okay, so we will focus on joins as well. And so the join trees, what I mean by join trees is just an ordering of the join, dictating how the join should be performed. In this case, R and S are joined first, and T and U are joined, and then the result of those two are joined together. Okay, so it's not necessarily dictating that this join is happening before this join. All that it's saying is that this join and this join happens first, and then this join is done. Okay, so that's all that it's saying. Okay, so this is one example of a join tree, and a plan corresponds to a join tree. And there are lots of join trees that you can enumerate in this fashion. Okay, so let's look at how these join trees might look like. A partial plan one that we're going to compute the cost of is nothing but a subtree of a join tree. So it's a portion of a join tree that we're trying to assign a cost to. Okay, so this is one type of a join tree. This is known as the left deep join tree. So here you have one, you're doing a join first and then taking the result of that join and joining that with the new relation, taking the result of that, joining that with a new relation, and so on. Okay, similarly, there's a right deep join. In this case, it's just that the left and right orders are flipped. So T and U are joined first, and then S is joined with the result of that, and then R is joined with the result of that. So the ordering can play a role depending on which join algorithm you are ending up eventually using. So for instance, if you're using a nested loops join, the left-hand side join argument is assumed to be the outer loop in the nested loops join. Okay, if you're using a hash-based join, the right-hand side is assumed to be the relation on which you compute the hash table. The left-hand side is the relation that you use to probe the hash table. Okay, so there are some conventions about this ordering in the join tree. We won't get into that, so that's not super important for our considerations. All that you need to look at right now is that there are many different join trees, and let's try to compute the costs of these join trees, or at least that's going to be our focus. So there's left deep, there's right deep, and there's bushy, right? So bushy joins don't just add one relation at a time to an increasingly complex expression. Here there are multiple subtrees that are themselves complex expressions that are joined together. Okay? So the join optimization problem that we're going to be focusing on is that we're given a query which is nothing but a collection of joins. So once again, we are ignoring selections, we are ignoring projections, we are ignoring other operations, we're just focusing on the joins. And we are assuming that we have a function that gives us the cost of every join tree, and we'll talk about what those functions look like. And our goal is to find the best join tree for the query. Okay, so in some cases, maybe the best join tree might be a left deep join tree with relations R1, R2, blah, blah, blah. Or in some cases, it might be a bushy tree with Rn, Rn minus 1, and so on, right? So it might be a bushy tree. And so our goal is, from among all of these join trees, which join tree should we pick? So trivially, look at the following issue, right? So if you have n relations, then even if I'm focusing just on left deep joins, so trees that look like this, there are n factorial different orderings of these n relations, right? There are n factorial different orderings of these n relations, and therefore there are n factorial different left deep trees alone, right? So that's a very large number. That's a very large number of just left deep trees. If you go ahead and add right deep trees or bushy trees, this number explodes even more. So once again, for right deep trees, again the number is n factorial. For bushy trees, the number may be even larger. Okay, so basically the issue is that there's a very large number of join trees, and our goal is to look at the cost of every single partial join tree and use those costs to assemble costs of more complex join trees. Okay? Any questions about this so far? Okay. All right. So just one step back about the big picture before I dive into how to find the best join tree. So we talked about vanilla translation into one logical plan. We talked about rewriting this logical plan. So we could use sort of rules that simply improve the expression, like pushing selection, simplification, getting rid of subqueries, aggregates moved up, and so on. So in some sense, you get a join tree with selections and projections and with other stuff above it. So you have a join tree with some selections and projections applied to the relations close to where the relations are read, along with other stuff that happens after the join. So that's our rule-based rewriting. So that gives us one join tree. Then the next step which we're going to be focusing on is the optimization of this join tree. and this is going to use a dynamic programming like algorithm, and this is going to give us an optimized join tree, and I'll explain what I mean by that. Finally, the last step is once you've decided on a join tree, you need to decide how to execute each join. For that, we need to specify the physical operation that is being used. So maybe a 2-pass hash join, or a sort merge join, or an index nested loop join, as well as the decisions that are being made, right? So whether you're going to be pipelining the results, whether you're going to be materializing the results, or maybe a bit of both. Okay, so that's going to be the last step. For now, we're going to be focusing on, given a collection of join trees, how do you find the best one? Okay, so that's going to be our primary focus for the next set of slides. Always end up making this mistake. Okay, so this was a problem. You are given a join expression, and I want to find the best tree for this expression. So the basic idea behind this dynamic programming algorithm, are most of you familiar with dynamic programming? Most of you have looked at dynamic programming in some class, right? Okay, so this is basically an application of dynamic programming, and the idea is simple. Even if you don't know dynamic programming or you've forgotten, the idea is very simple. The idea is that for every subset of relations, I'm going to compute the best plan for that subset. Okay, and then use those plans to compute plans for bigger subsets. Okay, so I'm going to look at these sets in increasing orders of set cardinality. So at step 1, I'm going to look at collections of relations of size 1. So these are all of the sets of relations of size 1. Then next step, I'm going to look at sets of relations of size 2. Finally, I'm going to look at sets of relations of size n, and this is where I'm going to get the final result. Okay, and when looking at step I, I'm going to assume that steps 1 through I minus 1 are complete, and therefore I can use either, you can think of this as recursion, or you can think of this as induction or dynamic programming. So step I can look at the results of step 1 through I minus 1 and use that to compute the best results for step I. Okay, and once again, for each step, I'm going to look at sets of relations of size I, and I'm going to compute the best way of computing the join for that set of relations. So this is a bottom-up strategy. So you are starting from the lowest possible sizes of subsets of relations, so sets of relations of size 1, and then using that to compute sets of relations of size 2, and then sets of relations of size 3, and so on. Okay? So now, how do I cost these steps? Okay, so the way to cost these steps, or the way to cost a plan, is, in this case, the cost of all of the intermediate tables in a plan. Okay, so it's going to be the cost of all of the intermediate tables in a plan, and so we are ignoring the cost of the final output. Okay, so the final output of R1 through Rn, the join, that is ignored, as well as the initial relations, the cost of the initial relations are ignored, because both of these are going to be common to all of the plans. So in some sense, if you think about, let's say, R1 through Rn, these are all being joined in some way. The cost of reading R1 through Rn is ignored in the cost of this plan, as well as the cost of the final result of computing the output. So both of those are ignored. All that is computed are the intermediate steps. Okay, so the intermediate steps in computing this final result. Okay, so, and the way to compute the intermediate step for an overall plan is, let's say your plan consists of part 1 and part 2 and a join of part 1 and part 2. Okay? So then the cost is the cost of the intermediates of part 1, cost of the intermediates of part 2, as well as the cost of this join between part 1 and part 2. Okay? And the cost of this join, the way I'm going to compute this is via the size of the joining relations if they are intermediates. Okay? So it's going to be the size of the joining relations if they are intermediate. So why do I consider that? So once again, the cost of a plan is the cost of all of the intermediate tables of a plan, and I'm ignoring the cost of the final table as well as the cost of the initial relations, because both of these are common to all plans. Okay? So remember, in the implementation discussion, we did talk about reading the relations because you might have ended up reading the relations multiple times. In this case, we are simply thinking about the cost of reading each relation once, and therefore that's a common cost that applies to all possible join plans. So we are not going to worry about that as much for now, and I'll explain the assumption behind that in a little bit. Okay? So we are ignoring the cost of the final table, we are ignoring the cost of reading the initial relations. These are both common to all plans. Therefore, the cost of a plan which contains two parts, part 1 and part 2, is the cost of the intermediates of part 1, cost of the intermediates of part 2, and the cost of the join. Okay? And the cost of the join is being approximated as the sizes of the joining relations. Okay, so it's going to be the sizes of the joining relations. And here, why are we considering the sizes of the joining relations? The sizes of the joining relations is in fact a lower bound on the join cost. Right? Because you have to read both of these relations at least once in order to compute the join. And therefore, the sizes of the joining relations is a lower bound on the join cost. Remember that in the implementations of the physical operators that we talked about, this could be 3 times that of the sizes of the relations in some cases. In some cases, it may be some product of the sizes, but overall, the lowest possible cost has to be reading each intermediate once. Right? So the lowest possible cost is the sizes of the joining relations. So the least cost of a specific join is at least equal to the sum of the two relations. This is the assumption that we are making. So in some sense, the overall cost that we are getting is a lower bound on the entire cost. Okay? So for now, we are not making an assumption about physical operators. We are just focusing on the join plan, and we are looking at the lower bound of the cost of each expression. For a lower bound on the cost of each sub-expression, we will use the sizes of the joining relations as a proxy for how much it's going to cost to evaluating them, because the sizes of the joining relations is a lower bound on the join, lower bound of the cost of the join. Any questions about this? Any questions about this stuff? I'll walk through an example and hopefully it'll become clearer. But for now, hopefully at least you understand what I'm saying, even though you may not agree with it. Okay? So let's keep going. Okay, so let's work through one example. Before I work through an example, I have to introduce the notation. So there are, so the essential idea behind this algorithm is for every subset of relations, we are going to compute the estimated size of the join of those relations, as well as the best possible plan for that set of relations. This is going to be a particular join tree, and the least cost for that plan. And the least cost for that plan is going to be the size of the intermediate tables used by the plan. Okay? And so all that we need to compute the final result are these three quantities for every single subset. We don't need to enumerate all possible join plans for each subset. We just need one plan which has the lowest possible cost, and we need to also record the sizes of that subset as well as that plan. That's all that we need to recreate the best join plans for the entire set of relations. So let's start with how you might do this. So the step one is to start with relations, sets of relations of size 1. So these are all possible sets with just one relation in it. The size of this join plan is going to be simply the number of blocks of that relation, okay, not surprising. And the plan for computing that relation is basically reading that relation, right? There are no joins, so it's straightforward. The cost of this computation is 0 because we are focusing on the cost of the intermediate tables, not on reading the relations. Okay, so we don't need to worry about the cost of reading the relations because that's going to be common to all of the plans. Okay, then we are moving on to step 2. Step 2 considers sets of relations of size 2. Okay, here the size of this set of relations is an estimate of the size of the join. We'll see how to do this precisely later on, but this is nothing but an estimate of the size of the join. The plan for computing the best way to compute R1, Ri, Rj, okay, so best way to compute the plan for Ri, Rj is either going to be Ri joined with Rj or Rj joined with Ri. Here we are going to use a convention of keeping the smaller table on the left hand side. And the reason why we are keeping the smaller table on the left hand side is there are various reasons. One of them is convention, so you can just do that and forget about it. Another reason is that when we are doing a join, we are usually representing the outer relation in the nested loops on the left hand side and the inner relation in the nested loops on the right hand side. And if you remember the physical implementation of the nested loops operator, the physical implementation always opted for the outer relation to be the smaller relation. So therefore, we will go with the explanation, or we'll go with the convention of keeping the smaller table on the left hand side. Although remember, right now we've not decided on any physical operator yet, right? So we are still working on the logical, we are still working in the logical space. But for now, we're going to make the assumption that we will stick to keeping the smaller relation on the left hand side, but there are some connotations to why we do that, and they can be explained by looking at the physical operators. But let's forget about that for now. Let's just go with the convention. The convention is we keep the smaller table on the left hand side. Okay. Now the cost of this is 0 because there are no intermediate tables that are used. Okay, so there are no intermediate tables that are used, and therefore the cost of this is actually 0. Okay. So next, for step I, what are we going to do? So given every subset of relations of cardinality I, I'm going to compute the size of this set of relations, and I'll tell you how to do that later on. Next, for every pair of subsets Q prime and Q double prime such that Q is equal to Q prime union Q double prime and Q prime and Q double prime, I want to do that. Q prime and Q double prime are disjoint. I'm going to compute the cost of computing the result of Q prime and Q double prime and then joining the two. So you can think of computing Q using all combinations of Q prime and Q double prime. Okay? So consider all combinations of Q prime and Q double prime and then doing the join on top. Okay? So how do you compute the cost of Q? To compute the cost of Q, it's a cost of Q prime the cost of Q double prime, and the cost of the intermediate tables that are used in computing this join. In order to do that, you have the cost of Q prime, the cost of Q double prime, and the size of Q prime and the size of Q double prime. These are the two components that are necessary to compute this join. These are the intermediate relations. However, if Q prime or Q double prime is a single table, then we won't compute its size, or we won't use its size. This is again following the rule that if you are reading one of the input relations, then that's a fixed cost that we don't need to worry about, and therefore we are not going to count its size. Okay? And then from among all possible breakdowns into Q prime and Q double prime, the cost, overall cost of Q is the smallest such sum, and the overall plan is the corresponding plan to that smallest sum. Okay? All right. So I think what I have next is an example. So hopefully that will clarify things. So in the end, my strategy is to simply return the plan for the entire set of relations R1 through Rn that has the lowest possible cost. Right? So that's what I'm going to end up returning. Okay. So let's work through some examples of this costing mechanism, and then we'll go into a more detailed example. So the cost of R5 joined with R7 is 0 because there are no intermediate results. The cost of R2 joined with R1 joined with R7. So I'm joining R2 and R1 first, and then joining that with R7. So using the expression that we had earlier, this is the cost of this guy, the cost of this guy, plus the cost of the intermediate tables. So I have an expression corresponding to the cost of the left-hand side, cost of the right-hand side, and the cost of the intermediate tables. Here you have one intermediate table. This is not an intermediate table. This is one of the inputs. Right? So I'm going to ignore its size. I'm only going to use the size of the left-hand side, which is R2 joined with R1. That is one intermediate table that I'm definitely going to have to compute. Okay? Then I get to this step, which is computing the cost of R2 joined with R1. Using this example here, I'm going to just say that this is going to be 0, so I can ignore it. The cost of computing a relation R7 is also 0 because R7 is part of the input, just one relation. So the eventual expression is R2 joined with R1. So another way to think about this is you can think about this as R2, R1, and then R7, right? And so you have a join between R2 and R1, and then a join between that and R7. Okay? So one way to think about this cost is nothing but what is the weight of all of the nodes in the tree that are not the root node. Okay, the root node is going to have the same cost. That cost is the size of R2, R1, R7 joined together. Here, there is only one intermediate node that's neither the leaf nor the root. That node has cost size of R2 joined with R1. Okay, so that's another way of visualizing or thinking about the cost of a join tree. So another, let's think of a more complex expression, right? So you had, let's say, okay. Let's say I had R1, R2, R3, R4, and I wanted to compute the cost of this expression. Right? Here the cost of this expression is going to be the cost of this intermediate table, the cost of this intermediate table, and that's it. The cost of this intermediate table is going to be size of R1 joined with R2, and the cost of this intermediate table is going to be size of R1 joined with R2 joined with R3. No matter which order we join, the size doesn't change. So these two are the two costs that are going to affect the overall cost of this join plan. That's another way of visualizing or thinking about this. Basically what I'm doing is I'm ignoring the leaves and I'm ignoring the root. Okay, so the root is ignored, the leaves are ignored. That's another way of visualizing how to compute this cost. Okay, so finally, this last expression is basically going to prove what I just wrote here. So I'm going to erase this and try to prove that. So if I have R2 joined with R1, joined with R7, joined with R8, okay, the first thing to notice is that this is consistent. This consists two expressions, this expression and this expression, that are being joined to each other. So this is nothing but the cost of R2 joined with R1. Maybe I'll get rid of one of these, joined with R7, plus cost of R8 plus size of the intermediate relations. The size of the intermediate relations is basically R2 joined with R1 joined with R7. Okay? So I'm going to say that this is going to be 0. The cost of this is 0 because R8 is the input. I'm going to leave this B, leave this expression B as it is. I'm not going to muck with that. Let me work on this guy now. So this guy, once again, borrowing the same rule, is going to be size of R2 joined with R1. So eventually I have size of R2 joined with R1 joined with R7. Okay, so this is the expression for the cost. Okay, so once again, if you think about it in a tree fashion, I'm ignoring all of the leaves, I'm thinking about the intermediate nodes that are not the root, and I'm computing the costs of the intermediate relations that contribute to that. Okay? Any questions about this so far? Let's get into a more detailed example that works out how to compute the overall expression. Okay, so for that I need to introduce some dummy numbers. So I have relations R, S, T, U. The number of blocks of these relations are 2000, 5000, 3000 and 1000. And I'm going to do a very, very crude size estimation. So we'll do a better job of this in the next set of slides. But this set of slides, I'm going to do a very crude size estimation. That's basically going to do the following. So the number of blocks in the join between A and B is 0.01 times B of A times B of B. Okay? So this is a very crude size estimation. It's basically saying take 1% of the result of the cross product between the two relations. That's going to be the estimate of the join. Okay? The setup is okay? Everything's fine so far? Okay. So let's get into the costing. So actually I'll show the expression and I'll try to explain some of them. So let's look at, the first step is of course to compute the sizes and costs of relations of size of sets of relations of size 1, but I'm going to ignore that for now. Those are the easy ones. Let's not worry about that. Let's start with the sets of relations of size 2. And the sets of relations of size 2, there are 6 of them. The sets of relations of size 3, there are 4 of them. And then there's one set of relations of size 4 because there are only 4 relations. Okay. So for the sub-expression R comma S, here what I want to do is to compute the cost of R comma S, size of R comma S, and the plan of R comma S, right? For the best plan of R comma S. Now the cost of R comma S, because R and S are both the input. So for computing R comma S, I have two alternatives. One is R is joined with S, and the other is S is joined with R. In this case, the costs for both of these alternatives are both going to be the same, that is 0, because these are both inputs. Once again, since I'm using the convention of which plan of the left-hand side of the plan being the smaller relation, here R is smaller than S. Okay, so I'm going to prefer R join with S over S join with R. And finally, for the size of R comma S, I'm going to use my formula. My formula says the size is 2k times 5k divided by 100, right? So this is going to be 100k. Okay? So now I'm ready to fill in this set of values. So the plan is R join with S, right, with the R on the left hand side. So the plan is RS. The cost of this is 0, right? So for both alternatives, R join with S or S join with R, it's 0. So it's 0. And the size is 100k. Okay? So let's pick another one and work through that also for size 2. Let's say I am trying, I don't know, what's a good one? Let's try SU. Okay, so for SU, I have two alternatives once again, S join with U and U join with S. Of these, U is the smaller relation, so I'm going to prefer U joining with S. Okay, so for U joining with S, I mean the size is going to stay the same independent of what you how you join, and the cost is also going to be the same. But either way, I'll talk about the cost and the size. Cost of both of these plans is both going to be 0, right? Because these are both input relations. The size are both going to be the same, and the value is going to be the size of S, size of U, divided by 100. That was the expression that we had. Size of S was 5k times U was 1k divided by 100. So this is 50k. Yes? Okay. So that gives us enough to fill up this row. So so for SU, the size is 50k, the cost is 0, and the plan is U and then S. Yes?
Wait, how do we get 100 again? Is it like part of the formula?
Yeah, so that was what I declared was the formula in the previous slide. So the size estimation is a bit crude, but it's basically 0.01 times B of A times B of B. Okay. So now let's assume that we've computed all of the expressions of size 2. I'm now trying to compute the expressions of size 3. Okay, so now things get a little bit more complicated. So I'm going to make some room. Okay, so let's try to compute, which of these do we want to compute? Let's try this guy. Okay, oops, I didn't want to erase. Let's try RST. Okay, so for RST, we have various alternatives. So alternative 1 is R join with ST, okay, or T join with RS, or S join with RT. Okay, so basically I'm breaking this up into sets of size 2 and a set of size 1. Now let's consider how you would compute the best results for each of these 3 alternatives. Yes?
Are you always putting the single table on the left side of the join? Because
No. I've not done that yet.
So we could still have ST join with R, for instance?
You could. I will consider those alternatives as well.
Okay.
Yeah. So all that I'm doing right now is to compute RST. I basically am saying that one of the relations has to be size 1, the other one has to be size 2. So I'm going to consider R and ST, and then S and RT, without specifying an order of the join yet. Okay, I'll get to that in a second. Okay. All right, so these are the three alternatives. Let's look at R and ST and how I might want to compute the best way of joining those two. The cost of joining R, so let's say this is, so if you remember the expression previously, you had Q here, this was Q prime and Q double prime, right? Now, if I wanted to compute the cost of Q using Q prime and Q double prime, the cost of Q using Q prime and Q double prime is nothing but the cost of Q prime plus the cost of Q double prime plus the sizes of the intermediate relations. Okay, so the cost of Q prime is 0, the cost of Q double prime is 0, and the sizes of the intermediate relations, here the size of this is ignored because it's the input. The size of this is cannot be ignored. It's the size of S joined with T. This can't be ignored, so this becomes part of the cost. Okay, so the size of S joined with T is nothing but what? So the size of S joined with T is 150K. Okay, so now if I were to actually join these two, I need to also specify an order of the joins. Here the size of R is 2K while the size of ST is 150K, so R will have to be on the left hand side of the 2, right? R will have to be on the left hand side operation of the join. So the 150K that I've come up with is the plan associated with that is going to be R with ST inside. Actually, in this case, it's TS, not ST. So let me change that. Okay? Good so far? Okay. So this is what I managed to get for R split into R and ST. Let me try another combination. Let me try S and RT. So here, once again, the cost is going to be the cost of one set of relations, the cost of the other set of relations, plus the sizes of the intermediate relations. In this case, the costs are both 0, and the sizes of the intermediate relations here, the size is ignored because it's S. Here, the size cannot be ignored because it's a join of two relations, so it's going to be size of R joined with T. Okay, so this is going to be what? Size of R joined with T is 60K. And what would the join, if I were to compute a join tree for this, what would this join tree look like? Any guesses? Yeah. Yep.
There'd be S and T, and then that would be joined with R.
S and, so S is going to be on the left hand side, and then within the parentheses what is going to be there? So R and T are remaining.
Isn't S going to be inside the parentheses and then R outside because T and S are being joined first?
So in this case, I'm trying to decompose it into S and RT. Now, in order to figure out which of those two should be on the left hand side, I need to look at the size of S and the size of RT. So the size of S is 5K, the size of RT is 60K. So I would keep S on the left hand side, RT on the right hand side, right? So, and for RT, the best plan is RT itself, so R joined with T. So it's going to be S in parentheses RT. Okay, so this was my second alternative, cost is 60K. Finally, I have my third alternative, which was T on one side, RS on the other side. Once again, the cost of this is 0 plus size of RS. Size of RS, I look up, size of RS is 100K. So, so this is going to be 100K. And what's a join plan going to look like? So using this, something that looks like this, any guesses on what the join plan would look like in this case? So once again, T is smaller than RS. So T should be on the left-hand side. And for RS, we need to go back and look at the plan that was listed, right? So the plan that was listed here is RS itself. So the plan is simply RS. Okay? Okay, so we have three alternatives, 150K for R and then join with TS, 60K for S and then join with RT, and 100K for T and join with RS. Of course, the one that we would like is the lowest, so that's 60K, that's S joined with RT. That is what I'm going to place here. So my cost is 60K and the plan is S joined with RT. Now I need a mechanism to compute the size. The size here is straightforward. Once again, you can think of this basically as B of R times B of S times B of T divided by 100 times 100, because there are two joins in this case, right? And so therefore I have, or another way to view this is as, so in this case it's S joined with RT. So you could also view this as B of S times B of R, B of T by 100. This is the size of join of R and T, and this whole thing divided by 100. Right? So these two expressions are equivalent. I just wrote the simplified expression. Is it clear how I got that size? Any questions about that? Okay, so now, so let me keep going. I'm going to pick another one of these to write out, but here I'm going to rely more on your help than me working it out. Okay, so let's try to do one of the other ones. Okay, so let's try, I don't know which one. Let's try this one. So RSU. So what are the ways I might be able to compute RSU? So what are the possible Q and Q primes that I want to consider? Yep.
R and SU, S and RU.
Yep.
And U and R.
Yep. Perfect. Okay, so let's start with one of them. Let's start with R and SU. Okay, I'm going to try to write that down here. Okay, so for computing the cost of R and then SU and joining the results together, what is my cost going to look like? So what's the cost? Yep.
I'm answering that. I have another question.
Sure.
Can't we look at the way we went about the previous one and kind of derive something from that? So we saw that S was the largest table there, and that came to the left, and then the smaller ones were in the bracket, and then those were sorted based on which was smaller in those. So S and then RT. So can't we apply something like that here and say that S would be outside the bracket, and then inside the smaller one, which is U, would be on the left, and then there would be R.
That's an interesting observation. So it might actually end up that in this particular case, those sorts of expressions might actually, those sorts of rules might actually end up working, except that that sort of does not explain fully why this final expression ends up being what it is. Because using your rule, you might end up with a left bushy plan, left deep plan, right? What you're saying is S join, so basically order it in increasing order of relations and then do joins. Is that what you're trying to say? Okay. So you're just saying from here to here I can generalize by saying that just like how I did in the previous case, the one that ended up doing the best was one with the largest relation on the left hand side. That might very well be the case, but let's work through it anyway. Yeah. So you might absolutely be right in this case. It won't hold, that sort of rule won't hold in general, just because, I mean, we have a counterexample with the final end product, because you don't really have you don't really have the left-hand side being the largest relation, right, in the final end product. It's actually a join, so it's actually a bushy tree. Anyway, so let's keep going, even though it might be might be actually obvious. So, all right. So R joined with SU. What's the cost of this? So the cost of joining two expressions is the cost of the left-hand side, cost of the right-hand side, and the size of the intermediate tables. So what would that be? So the cost of this guy, cost of this guy, and the cost of, or the sizes of the intermediate relations was what I explained earlier. So what would those be? Still zeros, right? So the cost of R is still 0 because it is an input. Cost of SU, you can look up this table. Cost of SU is already computed. You don't need to worry about it. That's 0 as well. And the size of the intermediate relations is simply the size of SU, right? And once again, you can look up the size of SU. That's 50K, right? So this is 50K, right? And so now you have the cost of R joined with SU. What is the plan, right? So the plan, we have two alternatives. So for SU, the plan was US. So you have either R joined with U and S, or U and S join with R. So these are the two alternatives, right? Either US join with R or R join with US. In this case, if you look at the size of US, that is 50K, the size of R is 2K, and therefore we are going to prefer this one. Yes? So this is going to be simply the cost of, so the plan corresponding to this cost is R with US in parentheses. Okay? So I'm not going to compute U with RS. I'll compute the last one because that's what is ending up being having the lowest cost, just as a counterpoint. So for this, the cost of S, the cost of RU plus the size of the intermediate relations is what we need to compute. So the cost is equal to 0 plus size of the intermediate relations. So size of RU, what is that? 20K, right? Where did I get that from here? Yes? Okay, so that's good. Now what are the possible join paths? So it's either S joined with RU or RU joined with S. And if you look at this table, table is telling you that for RU, the plan is actually U joined with R. So your two alternatives are S joined with U joined with R, or U joined with R joined with S, right? These are the two alternatives. Which of these do we prefer? The size of S is 5K, the size of UR is 20K, and therefore we are going to prefer keeping S on the left hand side. So this is what we're going to prefer. So this is nothing but S with UR in parentheses. So that's what we end up actually having as a final result here. And the cost of that is 20K, which is what we've ended up placing here. Now the size of this, many different ways of computing this. If you think of the size of this and you use this particular join path, you can think of this as B of S times B of UR divided by 100. This is equal to B of S times B of U times B of R divided by 100 divided by 100, which is equal to BS BU BR divided by 100 times 100. So just so that we confirm that this is indeed the case, so BU is 1K 10 to the 3, BS is 5K, so 5 into 10 to the 3, BR is 2K, so 2 into 10 to the 3, divided by 10 to the 4, so that is 10 to the 10 divided by 10 to the 4, which is 10 to the 6, which is 1 million, which is what we ended up adding here. Yes? Okay. All right. So this was expressions of size 3. I'm confident that you'll be able to sort of fill out the rest of the entries. Let's move to expressions of size 4. Okay? So what are the possible splits that we can have now? What are the splits that we can have? Into Q prime and Q double prime, without worrying about the order. Yes?
So we can have either one R and then STU, S and then RTU. So all those.
Oops. No, not RTU, UTS. Let's say S and then URT, T and then USR, and then U and then RTS. Okay? And then?
And then pairs.
Yep. And then pairs. So you could have US and then RT, UT, and then RS, UR, TS. Missing anything? Okay. So here we have 7 alternatives, right, to compute. So in the interest of trying to recover this one, I'm going to compute that one as well as maybe 1 or 2 more. So let's try to compute this one and this one. Okay? Okay, so but if I were to actually recover that this is the smallest, I have to compute all 7 of these. Okay, so it's fairly tedious. So let's try S with URT. Okay, so the cost of S is what? So the cost of S is 0, right? So I'm not going to write that. So the cost of S is 0. What is the cost of URT? 20,000, right? I mean, unlike sets of relations of size 2, when you're in sets of relations of size 3, the cost goes up. So in this case, it's 20K. Okay? Now, what is the sizes of the intermediate relations for S joined with URT? So you just need to worry about the last step because everything else is accounted for in the costs of S and URT. So the last step has 2 intermediate relations, S and URT. And URT, we need to just go and look at its size, right? So the size of URT is 0.6 million. Okay, so this would be plus 0.6 million. Okay, so that's its cost, right? So this is, so 620K, is that correct? Yes? Okay. Okay. So that's S joined with URT. Let's try another one. And so we don't need to worry about the join path for now. I'll get to that in a second. Let's try maybe which one was I wanting to try? Let's try this guy, UT joined with RS. Okay. So what is the cost of UT? 0, right? And cost of RS? Also 0. And the sizes of the intermediate relations? Sizes of the intermediate relations?
110,000?
110,000. How did you get that?
From adding up the sizes of US and RT?
Okay, so we are still in UT and RS, not US and RT,
Oh,
sorry.
sorry.
Yes, but you're right. So UT is 30K and RS is 100K. So it's 100K plus 30K. So this is 130K, right? Still not the smallest. So to get to the smallest, let's actually try the right answer, which is US with RT. For that, the cost of US is 0, the cost of RT is 0. And then the size of the intermediates are US is 50 and RT is 60. So the cost of this is 110K, which is smaller than 130 and is smaller than 620. Right? So we prefer this. This is the plan that we want. And I'll let you look at the other expressions to confirm that this is actually the smallest possible cost. Now let's look at the plan, the actual plan and how that looks like. Right? So we've decided that US with RT is the plan that we want. Now, in order to decide which ordering we want, we first need to compute the size of US and the size of RT. The size of US is 50K, the size of RT is 60K. Size of US is smaller than size of RT, so US is going to be joined with RT, right? And within that, for US, looking up the table once again, the plan is U join with S. So this is going to be U join with S. And for RT, the plan, looking up the table, is R join with T. So I'm going to replace this with R join with T. Okay? So this is precisely what I ended up getting here. So US on one side, and then RT on the other side. Each of them join with each other, and then you're doing the join of the results. Okay, so any questions about this stuff that's not clear yet? Yep.
So at a certain point there in the last step or two, we stopped doing the multiply the two block sizes together and divide by 100. Where did that step go?
Okay, we still needed to do that. So all that I've done here is to compute this guy and this guy. I haven't done that yet.
Oh, that's
okay.
For the size.
Yeah, that's for the size.
Okay. Right.
Okay, so I haven't done the size yet. Let's talk about the size,
Okay.
right? For the size, what I need to do is I've decided that I'm joining US first and then RT first and then doing the join of the two. In order to compute that, I need to look at the size of US, so that's 50K, and the size of RT, that's 60K, right? So that's 50K times 60, 50K times 60K divided by 100, right? So that's simply 30 million, right? So there's an ordering to this that makes sense as well. So you first look at the cost, figure out the best possible cost, you compute the best possible plan corresponding to that. You can compute the size at any time. You can start by computing the size because the size is going to stay the same independent of the order in which you join. Or you can wait until you've computed the best possible plan and then compute the size. Either way, if your size expression is as behaving as it shouldn't matter which order you do it. Okay, so in this case, we waited until we figured out the best possible join expression and then computed the size using that. That's totally fine. Any questions about this stuff? Okay. All right. So So this was dynamic programming for computing the best possible join tree. We started by smaller expressions of joins and then computed the results for larger expressions. We used pretty naive size and cost estimations in this. In practice, more sort of fancy mechanisms are used for both of these things. We'll try talking about some of those slightly fancier cost estimations if I get time, but probably not. Also, there are some heuristics that help us reduce the search space quite a bit. For instance, if I have cross products, I might want to avoid that. I might want to restrict it to left linear or deep trees. I might want to avoid bushy trees, for instance. Also restricted to sort of, like I said, trees without Cartesian products, right? So there may be heuristics that are used to reduce the search space. It's not our core concern. These are just things that database query optimizers do to sort of make it faster. So this is good to know, but not the focus of our class. Okay. Okay. So then let's talk about how to, given the best possible join plan, how do you convert it into a physical execution plan? Okay. In order to do this, we need to figure out how to implement every single operator in your query plan, and you may need to account for more than just cost, right? You need to think about how much memory do we have, and also potentially are the input operands sorted. So this is not going to be our core concern for the remainder of the lecture, because we are dealing with very, very simplified scenarios. So overall, one thing I want to caution you is this database query optimizer is a tremendously complex beast. Okay, so I've extremely oversimplified the problem in trying to present it to you, at least trying to present the core ideas to you. But the query optimizers are often hundreds of thousands of lines of code with very, very carefully designed rules and heuristics that try to optimize for things. I'm not going to be able to cover any or all of that. I'm just trying to give you the high level sort of concepts and ideas. Okay, so like I said, starting from a join tree, you need to decide how to execute that join tree, and for that you need to decide how to implement each operator, and also you need to decide whether for every intermediate result, are you going to materialize that intermediate result, so create it and store it on disk, or are you going to pipeline it? So is it just going to be stored in memory, and then is it going to be consumed by the next operator? Okay, so these are the two alternatives. So the first thing that we need to worry about is memory. The second thing that we need to worry about is what we need to do for each intermediate result. Are we going to store it on disk, or are we going to pipeline it? So are we going to create it in parts and move on to the next operation? So the entire relation may never be available, it may never be stored on disk. So let's take an example to talk about what these alternatives look like. And for now, I'm going to switch back to the realm of physical operators. So I'm going to talk about the actual costs of executing query plans, as opposed to the costs that we talked about for dynamic programming, which were the costs of the intermediates. So I'm going to talk about the actual costs as opposed to the intermediates cost. Okay. So let's take one possible physical execution plan for a left deep join tree. Okay. So I have this join of R, S, T, and U, and my join algorithm is basically saying, let me start by creating a hash table on S, and then I'm going to use R to probe S, and then write out the results of that join, and then create a hash table on T, read in the results of R join with S, which I'm calling V1, probe the hash table, compute the join, write it out as V2, create a hash table on U, read in the results of V2, probe the hash table corresponding to U, and then output the result. Okay. So said another way, let's walk through the code. So, or pseudocode. I create a hash table on S, I read in R, I join, let's say, tuple X from R with the hash table, compute the results, and then write it out. Right, write it out as V1. V1 is the intermediate result, so this is nothing but R joined with S. And I keep doing this until I've completed reading R. And then I create a hash table on T. I read in all of V1. I join one tuple at a time, the tuples in V1 with the tuples in T, and write out V2, which is basically R joined with S, joined with T. Okay. Then I read in U as a hash table, read in V2, which is R joined with S, joined with T, join the two, and then write out the result. Okay. So this is one possible physical implementation of this query plan. So what is the cost of this? Okay. So let's talk about the actual total cost of this. So the actual total cost of this would be, I am reading in and creating a hash table on all of S. So there's a B of S involved. I'm reading in all of R. I'm computing the joined result and writing it out to disk. So there's a cost of B of V1. So actually, let me just erase all of this. Okay. Just a few minutes more to complete this one example. So there's a cost of reading in R, cost of reading in S, a cost of writing out V1, and then a cost of reading in T, and a cost of reading in V1, okay, and then a cost of writing out V2, a cost of reading in U, and then a cost of reading in V2, and then eventually a cost of writing the final result out, which we are going to ignore. Okay, so this is the overall cost. So there's BR plus BS plus BT plus BU plus 2 times B of V1 plus 2 times B of V2. Where did the 2 times come from? Well, the first time I computed the result, I wrote it out to disk. The second time I read it back in and used it to probe the hash table. Right? So the overall cost here is B of S plus B of R plus B of V1 plus B of T plus B of V1 plus B of V2 plus B of U plus B of V2. This is B of R plus B of T plus B of S plus B of U plus 2 times V1 plus 2 times V2. The cost of computing intermediates is still proportional to what we had computed earlier. So this is 2 times one intermediate and the second intermediate. And how much main memory do we need? Here we need enough main memory to be able to compute a hash table on S or on T or on U. Okay, sorry, I had here S or T or U. For this we need the maximum of S or T or U. Okay, so an alternative to this is, if we had more main memory, is to do something much simpler, which is to compute a hash table on S, T and U at the same time. So 3 different hash tables. You read in R, okay, so you read in tuples of R, you join these tuples of R with the first hash table. Let's say the output is Y. You use Y to probe the second hash table. Let's say the output is Z. You use Z to probe the third hash table. Let's say the output is U. You finally write out the answer. So essentially, you are avoiding materializing the result here and materializing the result here, and instead pipelining through this entire process. So what is the actual total cost of this plan? The actual total cost of this plan is simply reading in R, reading in S, reading in T, reading in U. You're not writing anything in the middle here, nor are you reading anything in the middle. You're not writing anything in the middle here, nor are you reading anything. You're finally only writing the final result. Therefore, the cost of this is actually lower than the previous one. It's simply B of R plus B of S plus B of T plus B of U. And the cost of intermediates is actually 0 if you are able to pipeline through this entire process. However, the amount of main memory that we need is a lot higher. This is equal to the sizes of all of the 3 hash tables. So it's equal to BFS plus BFT plus BFU. Okay? So there are some trade-offs. I would prefer to do materialization and storing intermediate results into disk if I don't have enough main memory. If I have lots of main memory, I might want to pipeline through all of the operators and get a very, very efficient plan. Okay, so this is one example. I'll show you one more example on Monday to wrap up this topic.